Here are sample data that we will use to run a linear regression. And so we're going to compute a regression line that predicts y from x. And the data set that we are using has two variables. We have we will be using the number of hours of training to predict how severe injuries will be if someone is playing football. And so there's two variables in this data set. We have training, which is our x variable. This is also our independent variable, which is the number of hours per week of strength training. And injuries is our y, which is our dependent variable, and this is going to be the severity of injuries on a scale from 1 to 10. And so as we run this in SPSS, we will be checking our assumptions as well. And so our first two assumptions, we want to make sure that we have one independent variable and one dependent variable, and they're both measured at the continuous variable. And so we have met our first two assumptions. So now we can go ahead and start testing our remaining assumptions and running our linear regression analysis. So let's go to regression, linear. And so we are going to move injuries over to dependent. Training is independent. And let's go ahead and check for the following assumptions. So in order to do this, I wonder if I can create let me go ahead and do the others, and then I'll come back and create a scatter plot. So I want to test to see if there are any significant outliers using our case-wise diagnostics. So remember that a value of greater than plus or minus 3 is a common cutoff criteria used to define whether a particular residual might be representative of an outlier or not. And so let's go ahead and click on statistics here. Let's click on estimates. We want model fit. We want information on our R-squared change, descriptives, collinearity diagnostics, our Durbin-Watson statistic, our case-wise diagnostic statistics. We want outliers outside 3 standard deviations. So let's click on continue. Then let's go ahead and click on plots. So for y, we're going to put our z residuals here for y. And for x is going to be z predicted here. We want to click histogram, normal probability plot. Click continue. Now let's go to options, exclude cases pairwise, continue. We want our method to be enter, and we'll click OK. So we tested for all of the assumptions except for a linear relationship. And in order to do that, we need to create a scatter plot. So I'm going to go ahead back into my data. And I'm going to create a scatter plot. We'll click OK. All right. Okay, so if I'm looking to see if there's a linear relationship between our independent and dependent variables, it looks like there's a roughly linear relationship. It looks like there's a negative correlation between these two variables, meaning that those who, it almost seems like those who have more training Those who have more training have fewer injuries. Okay, which makes sense. Okay, so those who have more injuries have fewer hours of strength training. Okay, so let's look and see if we have significant outliers. Let's go to our case-wise diagnostics. So there would be a table that says case-wise diagnostics. And because there's no table here, that means that there aren't any significant outliers. And if you want to check this, if you want to go back into Analyze, Regression, let's go back to our data view. Linear regression here. If you want to check this just to be sure, so right now we're looking to see if there are any outliers outside of 3 standard deviations. I can change this to all cases, and if I click continue, it's actually going to run everything all over again. But if I'm looking for, here would be my case-wise diagnostics table, and I am looking at the column listed standardized residuals. This is where you're looking to see if there is anything greater or less than anything greater than a plus or minus 3. Okay, anything greater or greater or less than a positive 3 or negative 3 would be an indication of an outlier. As you can see, there is not. And so just in case if you were a little concerned because that table didn't pop up, that's because there were no outliers. So just a way to double check if you want to double check. Okay, so now I want to look for independent errors, and I can do that using our Durbin-Watson statistic. So if I scroll up here in my model summary, this is where my Durbin-Watson statistic is. It shows a statistic of 1.67, and so this statistic should be between 0 and 4. So we've met the assumption, okay? We don't have any independent errors. Let's examine our homoscedasticity. So this is where we plotted here. This is where we plotted our standardized predictive values and our standardized residuals. It created a scatter plot. This should have a somewhat rectangular shape. Okay, it's roughly rectangular, so I would say that we've met our assumption of homoscedasticity. And finally, I want to look at my histogram that's going to plot my distributed errors, and that should appear roughly normal, and it does. So we've met all of our assumptions. So now we can actually scroll up and look at our linear regression results. And this is where we're going to start in the model summary. So this is our first table in SPSS that we want to examine. This table provides the value of R and R square. And so for this data, R has a value of 0.458, and because there's only one predictor, this value represents the correlation between training and injuries, so close to a moderate correlation between the two. So our R squared, the value of R squared is 0.210, which tells us that training can account for 21% of the variation in injuries. There may be other variables that explain the variation, but in our model, which includes only training, can explain 21% of the variation. This means that 79% of the variation cannot be explained. Therefore, there must be other variables that have an influence also. The next part of our output reports an analysis of variance, our ANOVA table. And so the most important part of this table is the F ratio right here and the associated significance value of the F ratio. So for this data, F is 7.436, which is significant at P of 0.011. So the value in the significance column is less than 0.05. So we can conclude that our regression model results in significantly better prediction of injuries than if we use the mean value of injuries. So overall, the regression model predicts injuries significantly well. Next is our coefficient table, and where we can examine the slope. The slope would be right here. And so if training is increased by 1 unit, then our model predicts that injuries will be decreased by 0.125. And so this means that the regression line has a negative slope, since our slope is negative, reflecting a negative correlation of negative 0.458. Between hours of training and severity of injuries. So it appears, given the data, the more one trains, the fewer injuries occur. And that's what we roughly interpreted when we looked at our scatter plot as well. So going through a linear regression is sort of a lengthy process. There are more assumptions that you have to meet. There is much more output that you have to interpret. But I'm hoping that the Nearpod and the screencast has helped you get a better understanding of what linear regression does and how to interpret your analyses.